And I'm going to hand over the moderatorship today to my friend Todd Steeren, who is a BACCH user and has extensive experience integrating this technology into his system. Luckily, he lives near me, and I've gotten to hear it many times, and it is pretty fascinating and pretty amazing. So, Todd, I'm going to hand it off to you and let you introduce our speaker today.
Great. Thanks, Jim, and welcome everybody. As Jim mentioned, my name is Todd. I'm a member of the Audiophile Foundation for several years, and I'm very excited about who we have presenting today. As Jim mentioned, I am an owner. I come from a technology background. I have a couple degrees in engineering, so I'm very analytically, technically minded. And I got really serious about audiophile stuff about 15 years ago, and have built what I think most people would consider a pretty high-end, technically savvy first system. And I can tell you hands down in my 15 years, there has been no bigger impact on the quality of my sound than the BACCH system that Edgar developed. It truly is a highly innovative step change type of technology for the industry. And one of the reasons I'm so passionate, and, I spent my entire career in marketing. I understand the value of getting the word out. And I think when more people get the word out and they actually have a chance to talk about it, eventually listen to it, you can make your own decisions on what the impact is, but I think a lot of people will be surprised. I've been an owner of the BACCH system. As I'm sure Edgar will talk about, there are many levels within BACCH. I have the bottom, not the bottom, but towards the bottom level, called BACCH for Mac. And I've been an owner now a little under 2 years. So in 2024, I learned about BACCH because they won the Absolute Sound, called it the product of the year. And that got on my radar. And as I started to do some more research, I realized, oh, this is not like a completely new company. They've actually been around for a while. They've been developing this technology. And I went back and looked, and in 2016, they were best of high end from SoundStage Network. And then again, more recognitions in 2019. And then in 2022, there was an explosion of accolades. Products of the Year of Exponent and Capital Auto Fest and Golden Ear, a lot of recognition. And as you started to read some of the quotes of reviewers from these publications, they were, I mean, we're all used to sort of, hyperbole in quotes. But these sort of went even above that from what I'm used to. People that I respect were calling it, truly a breakthrough technology, groundbreaking technology. And the one from Stereophile publication that I think is a nice way to sum it up is prepare to be amazed. So it was with that I got involved and started doing a lot of research. And what I found out is that not only was the technology really interesting, but the man behind the technology was even more interesting. And we are very lucky today to have Edgar here to tell really about that journey and where is now. And as I thought about how to introduce Edgar, you never want to reinvent the wheel. And it just so happened that this morning I got my Absolute Sound newsletter. And what was one of the 4 stories that was being promoted? It was a story about Edgar and Theoretica Applied Physics, which is his company. And it was saying, is this the most innovative product in audio today? So when I clicked on that, I saw a great summary, and I thought I would just sort of explain what they said and steal from others that are watching this space. So Dr. Edgar Choueiri is the CEO and chief scientist at Theoretica, but he is also a professor at Princeton, where he heads up the Plasma Propulsion Laboratory. And his lab, that lab at least, is funded by NASA, and it's developing, engine science needed for interplanetary travel. But if that's not enough, because what would that have to do with audio? He's also head of the 3D acoustics lab at Princeton. And his funding there is partly from well-known players in the audio and automotive spaces, and it's to work on spatial reproduction. Edgar, besides the technological chops, obviously, is an avid music lover and audiophile, and he built this company, Theoretica Applied Physics, which sounds exactly like the name of a company that a professor would name it. He wanted to take his audio insights into the music at home world. And here I'm just going to quote directly because I think this is most relevant. Edgar realized that research over recent decades on how the ear and brain process audio was adding up to a set of insights that would allow computational correction of errors in the audio architecture. This is where plasma drive math skills and audio join forces. Theoretica mainly develops error correcting systems. That is to say, they are in the business of identifying systematic errors with the recording and playback chain. And then they develop solutions to correct or partially correct those errors. This is a radically different model than some of the enhancement system that adds to the, some kind of enhancement system that adds to the musical system elements that cover up or further distort the signal in an effort to be more appealing or exciting. So with that, I'm excited to welcome Edgar to our Audiophile Foundation event. We have up to 2 hours here. We'll go as long as this group wants to go. I've asked Edgar to put together a presentation roughly around an hour long. We're not going to take questions, during the presentation, but what you should do as you have them is throw them into the Zoom chat. And then at the end of Edgar's presentation, I'll start looking through there and we'll get through some of, all of the questions if we have time. And we'll hopefully have a really good discussion around that. So when we get to the Q&A, I think we can unmute if we need to allow people to have an interaction. But for right now, let's make sure everybody's muted. And with that, I will turn it over to Edgar.
Well, thank you, Jim, for the opportunity. Thank you, Todd, for this very generous introduction, very flattering. And also, I should mention that as soon as Todd invited me, there was no doubt in my mind this is a great opportunity. Especially, Todd is not only one of my savviest customers, he's one of the hardest to please. And he's, makes it, he throws all kinds of questions that make you really practice how to portray this correctly to people. And if I can sell it to Todd, then I can sell it to anyone. So it's good to have him as a customer first and as a link with this group. I should also say, as Todd mentioned, I am an audiophile. I don't get to speak as often as I'd like to audiophiles. Most of my talks are technical, academic, to groups and universities where people are working on spatial audio. And unfortunately, most of these people don't give a damn about a DAC or speaker, don't even own speakers, or care about music production at home. Ironically, a lot of these young people who are making these discoveries and driving this front end of audio, this bleeding edge of high technology in audio, are young people who are not audiophiles. I can tell you, none of my graduate students in this lab own speakers. Nonetheless, they are actually making breakthroughs. They are quite, their PhD thesis quite often have impact on things that we care about as audiophiles. So having the opportunity to tell you about but some of the ideas that come of my lab, which are in the context of spatial audio, that happen to be important for people like us who like about reproducing realistic music at home as realistically as possible, is a thrill for me. It's not something I get to do very often. So instead of having to delve into spatial audio in general, which is a very wide field in which I teach and we do research in, I'm going to concentrate on what's important for this group, which is two-channel listening. And within that particular domain, I'm going to concentrate on imaging only, mostly on imaging. I'll touch on other aspects later on, but mostly on how can we improve imaging in two-channel stereo. So for that, I prepared a set of view graphs, which I'm going to share right now. Here we go. And the title is 3D Imaging for Two-Channel Systems. Some of these slides were originally developed for talks on spatial audio, but I called them out, and I only kept a few that are relevant to my talk, and I added some that will illustrate the discussion. I want to first ask the question, what is spatial audio? Let me first tell you what my goal is. My goal is to convince you that stereo, as it was, so to speak, a two-channel, at one point, it is really a wonderful medium. Luckily, we have literally, since 1956 or so, almost all recordings were done in stereo. And so luckily, the information for us to get great imaging is in almost all recordings. So that's the big news. The bad news is that I'll try to convince you that stereo as it is, or as it was, is flawed in its capability of doing imaging. Now, there are many aspects of sound that we care about as audiophiles that has been improved tremendously. But I think it has been improved to the point where, at most, it's subtle improvements. And these incremental improvements have come to asymptotes, so to speak. While spatial imaging, which is the other leg of this being we call audiophile reproduction, is very short. It needed really, so we're walking on one leg, long leg, or one short leg, and needed an improvement to the point where it's now, I hope, is commensurate with the fidelity and tonal fidelity and time resolution. So spatial fidelity was lacking, and I will try to convince you it's an inherent flaw in stereo, and how crosstalk cancellation, which is a technique that's been known since 1961. I did not invent this technique. Actually, it was invented the year I was born, so I cannot claim it. But we've been lucky to improve on it and to make it transparent from a point of view of from a tonal point of view, to the point that it's not anymore curiosity in the lab. It is something that audiophile, the most requiring and the most discerning audiophile can accept it. Okay. So first question, I want to try to show you what spatial audio. Then I'm going to tell you how humans hear, and why is it that regular stereo, the way it is from two speakers, is flawed inherently in imaging, and how we can easily remove that flaw. Luckily, in using digital processing that only 10 years ago was very expensive, very difficult, and today is very easy and very easily to implement in any processor, and has no, also I'll touch on that, has no penalties on the quality of the sound. Now, what is spatial audio? I think it's best to simplify it into a caricature where you have two speakers, because we're going to stick with two speakers in this talk, and you'd like to reproduce a 3D image of a sound, let's say a bird in 3D space. Now, if you record a bird with stereo techniques and play it from a regular stereo system, two-channel system, what you get is a phantom image. The phantom image is mostly right where the speakers are. Irrespective of where the bird was during the recording, the image will be reproduced right between the speakers. We call that a phantom image. If you listen carefully to both speakers, the sound of the bird is coming from both speakers, and your brain is somehow putting the image in between, depending on the level difference between the speakers. Okay. Now I'll show you why this is a problem. The first, it's very clear it's a problem because the bird is being reproduced in the wrong place. So this shows you that as it is, stereo does not work in reproducing a 3D image. This is just the first pass. Now, people say, okay, well, we have surround sound. That's better. Well, it's not really better, because surround sound is going to give you another artifice to put maybe have more control on the location of the bird, but neither can it put the bird in 3D space, nor can it make it come close to you like in real life. It's more or less stuck to the speakers, just you have more speakers. So you can envelop yourself more speakers and move the bird artificially around, but that's not at all a reproduction of 3D reality. So surround sound is good for explosions in movies. So if you have five speakers surrounding you, it's great to have this effect for some content. But if you want to hear someone coming to whisper in your ear, you cannot do that with surround sound because the sources are stuck. Or if you want to have a bee go around your head, this speaker system by itself cannot do that. Okay. So the question is that how can we get a bee to go around your head from two speakers? How can we record it and play it back so you can hear a true 3D image being replicated at your ears like it was in real life? It turns out that there are three methods to do that. And I'm not going to talk about these three methods except say very few words about each, because the first two methods are completely useless for us as audiophiles. They each require many, many speakers. That rules them out. How many speakers? As many as you can throw at them. Ideally, infinite number of speakers, but at least 20 speakers to get wave field synthesis and ambisonics to give you a good 3D image. Plus, that's the big plus. That's the big minus, I should say, is that they also require that you record in a certain specific way using many, many microphones. How many? Again, ideally, infinite number of microphones, but typically 24, 36 microphones are needed for many of these techniques to start giving you a 3D image. That makes them completely useless for us as audiophiles because we want to listen to already existing stereo recordings. So if we restrict our scope to already existing two-channel recording and they require only two speakers to play back, we can throw away these two methods out of the window. But before we throw them out of the window, I'll say a few words about them because it's good to know that there are references. Second, I should tell you that although as audiophiles we've thrown them out of the window, these two methods, especially the second one, method 2, is already integral as part of gaming and virtual reality and augmented reality. They use them luckily because you can do a lot of these artificial recordings, not with actual microphones, but with digital microphones, with imaginary computer microphones, and reproduce them with, again, digital speakers on computer. So let me first describe briefly what each of these two methods and concentrate on the binaural crosstalk cancellation method, which is relevant for audiophiles. So method 1, the idea is that if you have a point source like a bird and you want to record it, the simplest idea is you have a number of microphones that will capture the sound wave. These are the typical sound waves coming spherically from a point source, and the black part are the microphones. Now, if you then take those recordings and somehow play them back, all these multi-channel recordings from each mic, you have a single channel, feed them into an array of speakers that's arrayed in such a way to reconstruct the wave field. We call that wave field synthesis. You can, in principle, make someone believe that they are listening to a bird. So imagine you have a bunch of speakers here. You can recreate the same wave field structure that the bird will create. As you can tell, this requires many, many speakers. And as I said before, a special recording technique. How many speakers? This is a typical system. This is a system in Germany. There's one in RPI that has Rensselaer Polytechnical Institute in Troy, New York, that has hundreds of such speakers. The Sphere in Las Vegas has similar wave field synthesis system with thousands of such speakers. But I don't see any audiophiles, partner or wife, tolerating such a system in any home anytime soon. So this is, again, out of the window for us. Now, higher order ambisonics is a more compact, more ingenious way to do the same thing, developed by a mathematician in Oxford in the 1960s by the name of Michael Gerzon. It requires using a special mic that actually has many mics on it. As a matter of fact, right here, I have one such mic. You see it right here. And that mic is called a higher order ambisonic mic, and it would it has 24. This one has, I think, 24 or no, 32. And I have another mic that has 64, a new version. And using some complicated mathematics, you can actually record the sound field on a sphere instead of having microphones around the room. And then you can reconstruct the sound field from many speakers using mathematical transformation techniques that are called higher order decomposition, spherical, harmonics. All of that is beyond the talk here, because again, to do HOA correctly, and you need to surround yourself from speakers. Imagine sitting in the middle of a sphere of speakers. Now, if you come to my lab, we have such systems. We can show you what they can do, but there are no interest to audiophiles. So, is there a simpler, more elegant and natural method, and one that's compatible with existing recording? The answer is linked to how we hear in 3D. I'll try to convince you now that if we understand how humans hear in 3D, and again, I presume many of you know some of these fundamentals, but once we go over them, we'll see how stereo has the potential, or two-channel recordings, the potential to portray a very realistic 3D image. Now, I'm going to concentrate today on acoustic recordings because they allow us to explain how this realism, how 3D imaging can occur realistically. However, everything I'm going to say is relevant to, and I'll say a few words about that later on in the discussion period, is relevant to fabricated recording, to recording that are done artificially by mixing in a studio. Okay, so let's first understand how we hear in 3D. We hear in 3D because of three types of cues, spatial cues, that our ear-brain system interpret as localization cues to locate sound. So the first kind of cues are called ITD, interaural time difference. If someone speaks from the right, it takes a little bit longer for the waves to arrive at the left ear than the right ear. So you can see that time 1 and time 2, these are time of arrival of the wave of that speaker, of that person speaking to your ears. And your brain can detect these tiny differences in time. It was almost irrespective of age. You can hear then down to almost 10 microsecond difference between left and right ear. And your brain is very good at locating sound, especially at higher frequencies. With these ITD cues, interaural time difference cues. That's not the only cue, of course. The other cue is even more obvious. If somebody is on the right and speaking, the sound on the right ear will be louder than the left ear, mostly because it arrives earlier, so it's not as attenuated, but mostly because it's the head. The human head is going to create a shadow. So if something is on the right, it's because of the fraction around the ear, because the ear is stopping the sound to come clearly to the left ear, you get more intensity on the right ear than the left ear. Therefore, we call that interaural level difference. Your brain can detect interaural level difference down below 1 decibel and to locate sound in 3D space. And our human brain ear system is very powerful at detecting these ILD, ITDs in order to survive. As a matter of fact, evolutionarily, this is how we located danger of the proverbial bear coming at us from the forest to locate sound. Now, it turns out there's one more cue. Before I explain that spectral cues, what spectral cues are, let me show you what the problem is. The problem is that ILD, ITD are not enough. Imagine someone is sitting in front of you and making a sound, singing or clapping. There's no ILD. The interaural level difference, if it's perfectly symmetric, is 0 in the right and left ears. And also there's no ITD. The waves are arriving at the same time in left and right ear. Therefore, the brain cannot use those cues. Somehow, the brain must be using some other cues, because we can easily locate sound even if our eyes are closed. If someone is standing right in front of us, especially if somebody goes up and down, we can tell. We can tell very much if they're behind us or in front of us. That has to do with something else. They must have to do with something else other than other ITD, ILD, and that's called spectral cues. That's the fact that the ear itself, because of its shape, it's called the outer ear, the pinna, causes diffraction of the sound as it enters the ear canal in such a way as to color the sounds tonally, so it requires a certain tonality depending where it's coming from. So and also it depends on the shape of the ear. Here are different shapes of ear. Unless if you have an exact twin, you have it's like a fingerprint. You don't have the same ear, and everybody's ear imposes a different tonal signature called the head-related transfer function, or HRTF for short, that allows your brain to judge from the coloration where the sound is coming from. If you bend your ears, if you deform them, you start committing errors, especially at higher frequencies, at locating sound. And these cues are very important for height information because, again, as I mentioned, the ILD and ITD cues are useless because they're zero in the medium plane. So your brain is going to rely on them a lot, especially for points in space where the ILD, ITD cues are either ambiguous or do not work. We call that cones of confusion. But the bottom line to retain from all this, that ideally we should record ILD, ITD in spectral cues and reproduce them correctly to a listener in order for the listener to get a 3D image. But how are we going to do that? Well, the best way to do that is to mimic something called a stereograph. And that goes back to the 1840s, even actually 1830s, where someone wanted to create a 3D image. And this gentleman, a Scottish engineer by the name of Blackstone, I think. Bottom line is that that gentleman decided to make a drawing from the left ear's perspective and make it presented to the left ear, and make a drawing from the right ear's perspective presented to the right ear, so humans can see in 3D. When he did that, he couldn't see in 3D until he stopped the right ear from seeing the left image and the left ear from seeing the right image. And only then he saw in 3D. Why is that? It has to do with the fact that in order to get perspective correctly, you need to present to the ear, to the eye, the correct information for your brain to have the perspective, to reconstruct the perspective correctly. So there are two vantage points for the two eyes, and that interocular information, which we call perspective, has to be reproduced at the ears correctly. And if you allow the right ear to see the left image, it will destroy that information because you're not now anymore maintaining the interocular information. And if you do that by putting what we call a cross-site canceller, this little board between the images, and that's been known since the 1840s. That was developed even before the invention of photography in 1837. In 3D audio, we can do the same thing if we record and capture the ILD, ITD cues, and spectral cues, and then be able to reproduce them from two speakers such that they're reproduced correctly at the left ear and the right ear. Okay. The problem is you have to make sure that the left channel information, which has to reproduce the sound recorded at the left ear, is reproduced at the left ear only, and the sound on the right channel, which is recorded by the microphone on the right ear, is reproduced at the right ear of the listener only. Only then the ILD and the ITD cues will be reproduced correctly, and only then you will be able to locate the original recorded sound source in its correct place in 3D space. So we call that a crosstalk canceller, which is a perfect analog to the cross-site canceller that exists in 3D imaging. Now, if you translate that into an ideal recording, so we want to record someone there on the right, we put microphones, ideally inside a head, but at least spacing that resembles head spacing, and record the sound and in 2 channels. That captures the ILD, ITD. If you play it now from 2 speakers, the fact that the left ear is going to hear signal from the left channel and from the right channel, that ruins the interaural time difference and interaural level difference. So that's called a crosstalk. In order to preserve the, if that happens, you'll hear the speaker, the singer coming from the right channel only, until you put a way to crosstalk cancel the signal. In other words, you stop the right signal from reaching your left ear. Only then that differential information between left and right ear will be restored. And I'm going to illustrate this in more view graphs. But the bottom line here is that in order for us to be able to reproduce the interaural level cues, interaural time cues at the 2 ears of the listener from 2 speakers sitting in front of you, you must ensure that no sound from the left speaker reaches the right ear. If not, your brain will locate the left speaker and will not locate the original source. Okay, so let me illustrate that more accurately. Imagine we have a left and right channel. We're going into recorded regular stereo recording, which is now going into playback system, which has no crosstalk cancellation. In other words, just the playback left and right, and go into 2 speakers, and we have a human head with 2 ears listening to that. Suppose we now put a signal, let's say pink noise, in the right channel. So that pink noise comes through and played back. There's nothing on the left channel, so only the right speaker is going to make sound. So if you ask a listener, where is this sound coming from, that listener is going to point to the right speaker, because the sound is coming from the right speaker, and that the right speaker is sending waves to the left and right ear. So the difference between the left and right ear level is typical of a speaker in that location, which is about 4 to 5 decibel. If you put the speaker at plus or minus 30 degrees, you get 5, let's say 5, if you put the speaker at around 5 degrees, 30 degrees to the right, the sound will be about 5 decibel louder on the right ear than the left ear. You can actually measure that. Actually, BACCH DSP is software that I developed, measures that. This is a measurement done exactly by putting pink noise into, or a signal or a sweep into the right signal and right channel, and measuring the difference between the right ear and left ear in decibel. And you'll see at low frequency, it is lower than 5 dB. At around 1 kilohertz, it's about 5 decibel. Above 1 kilohertz, it goes, up to 10 dB, but not more. In other words, your brain, this system can only reproduce at most a signal that's locked to the right speaker on the right, and the same thing on the left, a signal that can be locked to the left speaker. Now, the fact that you can go above 5 dB at above 1 kilohertz, that is due to the fact that your head is causing some crosstalk cancellation. Your head is stopping some of the sound at high frequencies from reaching the left ear from the right channel. That's called head shadowing. So you have some effective natural crosstalk cancellation, and that leads to the ability to the system to reproduce a bit more than 5 dB at high frequencies. But generally, on the average, this is not going to produce more than 5 to 7 decibel crosstalk cancellation. ILD. Now, what does that mean? That means if you have a bird, and the bird is sitting all the way to the right here, from the 2 microphones, left and right, that if you measure the difference at the microphones, it's 12 decibel. In other words, if you're sitting where the microphones are, you will locate the bird all the way to the right, almost at 3 o'clock. That's because there's so much more difference, so much louder, the sound is so much louder at the right ear than the left ear by 12 decibel, and your brain would put the bird right there. If the bird is about 20 decibel, it can be right at the right ear. Your brain knows there's almost nothing at the left ear. The bird must be sitting right by the right ear. This is how we locate that sound. Now, if we take that recording and play it with the system with no crosstalk cancellation, whose ability to reproduce ILD is shown in this plot on the right, you can see that the most the bird can be is in the right speaker, because the most that system can deliver to your ears is an interaural level difference of 5 decibel. Therefore, it's flawed. that playback system is incapable of reproducing the interaural level difference over the real sound in 3D. So if we replace the bird with a band, so we start with a jazz band where we have a singer in the top, and then let's say the drummer and the piano and bass are not only to the right and left, but they're also forward in the room, in the studio doing the recording. So they are standing almost at 3 o'clock and 9 o'clock or into the room or somewhere there. And you want to reproduce that 3D image with the layering, with the exact positioning of the instruments. If you play it with the left and right channel, because the system cannot reproduce more than 5 decibel, therefore, it's going to reproduce the rightmost image of the rightmost source, which is the drums, is going to be coming from the right speaker and not more than the right speaker. Now, because, as we saw from the previous plot, there is some crosstalk cancellation above 1 kilohertz, the image, especially the high frequency part of the drum, is going to extend a little bit more than the right speaker. This is why you hear this, more 3D imaging from regular stereo. It's because the higher frequencies are crosstalk cancelled naturally by your head. But still, the image becomes flat. We call that a phantom image, and it becomes completely locked where the speakers are. As a matter of fact, we all know that if we take those two speakers and make them collapse the angle between them down to 0 degrees, that jazz band will collapse to a single point. And if you spread it all the way to, let's say, 70 degrees, it becomes wider, but we have some problems with the center image. So the compromise is somewhere plus or minus 30 degrees. That's the regular stereo triangle that we are advised by audiophile gurus to maintain. Now, that is a compromise, and that is an index, or there is a manifestation of the flaw in this kind of stereo reproduction, the fact that the image is locked to the speakers. If we can develop a system that can reproduce the image correctly in 3D, the speaker position should have no influence whatsoever on the position of the instruments. And here I'll do some fast forwarding and tell you that with BACCH, quite often we do that at shows in order to drive a point. When people ask us where should we put our speakers to get the best effect with BACCH, the answer is to a 0th order, unless if you're impacting the reflections in the room. You can put them anywhere. You can put them touching each other. So you can put the speakers at 0 degrees touching each other, make a BACCH filter, which we're going to talk about in a few minutes. And then if that technology does the right job, you should reproduce the musicians irrespective of where the musicians are or the speakers are. So the drum will come exactly where it was, appear there, and the piano and the bass, irrespective of what the position of the speakers are. And that's exactly what happens with BACCH. But it's clear right now, before we get to BACCH, that does not happen. We all know that does not happen with regular stereo, because the image is locked to these speakers, because of the inability to deliver more than the maximum interaural level difference that a single speaker can deliver. So the right speaker can most deliver 5 decibel or so. The same thing for left speaker. The image is going to be restricted there. We call that a phantom image. That means our brain is locating the instruments and the musicians based on the interaural level difference of the speakers, not based on the interaural level difference at your ears, which it cannot reproduce. Therefore, we are reproducing what's called a phantom image. In other words, instead, if a bird is coming at you, you locate that bird because of the interaural level difference that happens at your ears. And here, this kind of stereo reproduction is as if you have 2 birds coming at you and both are singing, and somehow the one is singing less than the other, so your brain puts the image artificially between them. That's not what happens in real life. So the stereo reproduction without crosstalk cancellation is completely artificial and completely flawed. Now, of course, this is all clear if we're doing acoustic recording. I'm sure somebody's going to ask me what's going to happen if we're doing concocted recordings, and we're going to come back to that later on. But let's finish the discussion with acoustic recordings, and then go back to what happens if we now have a system that can cancel the crosstalk. I'll say how crosstalk cancellation can be done, but let's assume we have such a system, and this is the performance of a crosstalk cancellation filter, a BACCH filter. And now instead of having 5 decibel going to about 7 decibel, BACCH filter can do crosstalk cancellation up to 20 decibel. In this case, average of about 20 decibel, at least starting about 15 decibel at 200 hertz and going up. That means if we put a signal in the left channel and the right channel and the left channel, we can now deliver up to more than 15 decibel. So now the drummer, who's at 12 decibel interaural level difference, has no problem being reproduced because the system can deliver more than 15 decibel crosstalk cancellation. So now, because we are blocking the sound from the right speaker to reach the left ear, you're not anymore locating the right speaker. We can control the level at your ears. So whatever is recorded on the right microphone and the left microphone as pressure in time, that history will be reproduced at your ears, as if you're wearing headphones. Now, headphones have their own problem. We can talk about that separately. I know headphones are not very popular among many audiophiles above a certain age, including myself, although we have a headphones technology. But headphones do not have crosstalk, but they have other problems when it comes to 3D imaging. So let's stick with speakers. With crosstalk cancellation, we're able to deliver pretty much by eliminating that cross path between the right speaker and the left speaker. We can now control the right and left pressure so that we transmit to them pretty much what on the right and left channel of that recording. So if there was somebody standing producing 12 decibel on the right, level difference between the right and left microphone, that musician will produce the recording of that musician will produce the same pressure level, and your brain will put that musician exactly where they were standing. So that solves that problem, at least for the ILD. It turns out that ITD, and I'm not going to go through that, is a little bit less intuitive, but it works on the same exact principle. It's also corrupted by the fact that you have crosstalk. And if you remove the crosstalk, you can also deliver the interaural time difference to the ears more correctly and reproduce sound in 3D. So that works beautifully for all stereo recordings, because all stereo recordings are either based on ILD or ITD. Now, all acoustic recordings are either done with what's called spaced omni techniques, which are spaced omni microphones that capture the interaural time difference. These are 2 microphones that are omnidirectional. They are spaced a certain distance apart, and you rely on the difference in the time arrival to create a stereo image. If you play them through a BACCH filter, a crosstalk cancellation filter, your brain will get far more fidelity in the transmission of this interaural time differences, ITD differences, cues, than it would if there was no crosstalk cancellation filter. Because if there's no crosstalk cancellation filter, the image will collapse into the speakers like a phantom image. So the other technique is where you use coincident mics, which are cardioid mics that's used for acoustic recordings, and they rely on the ILD. And I'm not going to go through microphone techniques, but this is quite often used in classical music and acoustic music. You put 2 microphones touching each other, but they are inclined with respect to each other. So they have cardioid directivity pattern that allows them to differentiate between left and right based on the interaural level difference. Again, when you go through a production system like BACCH, this will be reproduced at your ears with the correct ILD level, and you get the 3D image. So all ID recordings, they are done with stereo microphones, unless they're really messed up by phase problems. They should give you significantly more realistic 3D imaging if you play them through a crosstalk cancellation filter. If the crosstalk cancellation filter gives you high enough crosstalk cancellation level, and if it doesn't do anything bad to the sound, which is the big if. And this is where BACCH comes into play. Okay, so now I'm going to say, how does BACCH filter work? How can it do that? Now, I'm not going to go through the math behind it, but just simply spoken, the BACCH filter has let me first put this here. Okay, so the BACCH filter can be derived mathematically, and there are textbooks now describe it, from modeling the transfer function. This is using language from control theory between two speakers and two ears. And here you see schematically how acousticians or physicists and engineers derive these models. And the idea is to derive a filter so that when you put a signal into that filter, left and right, somehow only the left signal appears at the left ear and the right signal at the right ear. And that can be paused mathematically, and that can be solved mathematically. And you can arrive at a solution. And instead of going through the math, I'm going to describe that solution physically, what it means. This is the impulse response of a crosstalk cancellation filter, which if you convolve with the stereo signal, will give you that sought-after crosstalk cancellation we have been discussing in the previous view graphs. Namely, if you put that, if you add that by convolving it, meaning by adding it to your sound, somehow this is a technique called convolution, which means that you filter the sound through this filter. Your ear will get only what's on the right channel will only leave on the right. Your right ear will hear what's only on the right channel, and your left ear will hear only on the left channel. How could that be possible? It's possible because that filter does act the following way in real time. What you see on this plot is time on the x-axis. It doesn't matter what units, it's a time. And let's say they're on the order of actually microseconds, which is not bad, not incorrect. And the y-axis is the amplitude. And these are the black dots is what the left speaker is doing, and the right dot is what the right speaker is doing. So this impulse response results if you put a click in the left speaker. If you put the click in the left channel, rather, if you put the click in the left channel, crosstalk cancellation, if it works perfectly, will make your brain believe that it's only at your left ear, as if someone just clicked at your left ear, even though the two speakers could be many feet away from you. How could that be done? Well, that could be done if this. For that to be done, the filter will send first a click, that first black dot on the left, to your left ear. It will arrive there. If the world stops right here, your brain thinks someone is at your left ear. But that doesn't happen because that sound will reach your right ear a few microseconds later, about 10 microseconds later. And that is the crosstalk we want to kill. Therefore, the filter will send that white dot in the bottom, that first white dot, that white impulse, a little white circle, that comes from the right speaker, delayed in such delta t to arrive at your left ear and kill that sound because it's inverse phase. It's basically inverse the phase and sends that image to the left speaker, to the left ear, to kill it. However, I'm sorry, it was sent to the right ear to stop it. So that basically your brain will only hear the left ear. Again, if the world stops here, you will think someone is clicking at your left ear. But again, nothing stops that wave that the right speaker sent from arriving at the left ear. Therefore, you need to cancel that. And therefore, the filter instructs the left speaker to send another black dot impulse timed correctly to arrive at the left ear and cancel it. And so on and so on. Luckily, you don't have to do that many times because as you do it, the volume we need to do that cancellation becomes less important because of the head shadowing. And only about 20 or 30 such cancellations are enough to completely cancel everything except the first black dot. So your brain gets only the information at the left ear, meaning that as if someone makes the click at the left ear. So somehow now, because of this filter, if somebody put a click in the left microphone, it will appear not on the left speaker, it will appear at the left ear. Because all the other arrivals of that sound to the right ear are being canceled. And all the cancellation signals that are being sent to the left ear, which also are not needed, are also be canceled. That works perfectly, but only in a perfect world. It turns out that the problem with this perfect filter, which exists since 1962, not digitally but analog back then, is that that filter, as we call it a perfect filter, has a horrible frequency response. It sounds like this. This is the frequency response from 20 hertz to 20 kilohertz. And as you see, it has these horrible peaks and a big boost in the bass. No audiophile in their right mind will allow this to be in their system. As a matter of fact, this is why crosstalk cancellation remained in laboratories for decades as a curiosity before it was before the problem of tonality. This is before the problem of this horrible spectral coloration had been solved, which is what the BACCH solution is about. So the reason why this is so has to do with the fact that these cancellation waves happen when they arrive at your ears, they cause a destructive pattern, and there are some points in space where the amplitude has to be boosted, some where the amplitude have to be turned down in order to cause the cancellation. And therefore, the filter has to do a lot of work and cause a lot of coloration, which will only sound perfect if you are sitting perfectly aligned with speakers, so perfectly aligned that it really cannot be done practically. This is what we call that a perfect filter. So what BACCH does is a technique that now is patented and is now taught in textbooks that allows to inject a certain error in the design of the filter to push the control perfectly into the not perfectly, mostly into the phase domain, so that the frequency response in the amplitude domain can be completely flattened. Now here it can become too technical, but all I want to show you is that the BACCH filter in the time domain does not resemble anymore that neat train of delta functions I showed you before. This is how it looks. It looks a little bit messy, but actually the net result of which that only a single impulse survives. And then the frequency response of that is a perfectly flat line, 0 dB across from 20 hertz to whatever Nyquist frequency you have, 48 kilohertz. You have perfectly flat response, meaning the filter does nothing whatsoever to the sound. And that is what allows us to get a patent on this approach. How to design a BACCH filter is patented. And the main key by the BACCH filter is that it does not cause crosstalk cancellation only because that's been done before, but it does it without any coloration to the sound. It's perfectly transparent. By perfectly, I mean exactly flat, ruler flat frequency response. We call that a BACCH assembled crosstalk cancellation hierarchy, band assembled crosstalk cancellation hierarchy, and we came up with BACCH, my favorite composer, and we call that the BACCH filter. And then the university has since patented it and licensed it for a number of companies. My goal as an audiophile was to take it from the lab and not to commercial audio. As a matter of fact, the biggest moneymaker has not been the audiophile community that I belong to, but has been the consumer audio. The BACCH filter first appeared in Bluetooth speakers called the Jambox. They sold millions of them. The university gave me a share of the royalties that I took 100%. Instead of asking investors, I put all the money in creating an audiophile company called Theoretica, so I can get that technology to the homes of people like me who care about listening to sound. So this is where Theoretica comes into the discussion. So I'll finish by saying a few words about the company and what it does. So first, initially, I created a no compromise processor that can, based on in-ear microphone measurements. If you go to the website, there is a flyer that you can see in PDF, but it looks like it's all controlled by an iPad. It's called a BACCH SP. It comes with in-ear microphones, which you put in your ears like this, and you sit in front of a camera and your any two speakers, and you do a calibration using the iPad by clicking a couple of places. And then basically you get very high level of crosstalk cancellation, as much as your room allows, that allows your imaging to be significantly increased. Now, the first time we did that, it was done, by the way, all these units are built here in Princeton. The first unit we built, if I go right here, the BACCH SP in 2014, was so involved and it's all handmade, hand-wired. By the time we tally it up all the time, and without being outrageous in our markup, because dealers were involved, this came up to a huge amount of money, $54,000, and it was ridiculous in my book to sell something like only option. And I wanted to go I set a goal to myself that if I have a technology that comes out of my lab where graduate students work, I want them to be able to afford it. At least when they finish and get a job, they can afford it. So I created on the other end of the spectrum an alternative from this BACCH SP grant called BACCH for Mac, which actually starts at $980. And it's purely software. I'm going to show it to you. As a matter of fact, somebody, before I started the talk, just bought it in India. And this is a BACCH for Mac intro. It's $980, and it gives you a very good approximation of what BACCH can do. This is not the low level that Todd mentioned earlier. Actually, what Todd mentioned is a pretty high level. It's the next step up, which is a huge step up. I filled these two bookends, the intro and the grand, with as many options as I can possibly do and retain value for people. So the BACCH for Mac intro, which costs $980, allows you to experience crosstalk cancellation very easily. The software does not require any hardware beyond your DAC and your speakers and your preamp. It does require a Mac. And you plug it, you download it, and we will help you through it. For every customer who buys it, we have a time unlimited walkthrough session that either myself or my assistant John now gives. Most of the time I give it. And it requires that you actually hook up your system to the software, and you click on ARM. And in this case, I am going to actually show you how to use the UBACH, which is the universal BACCH filter, which is the intro level without any measurement. You click on ARM, and then you dial the distance between your speakers and the distance between you and the speakers. Okay, so in here I can make that like 159 centimeter, and this is, you just measure it with a tape measure. That's all you have to do. And you click on fire. That will print in this bin number 1. This happens to be 30 degrees, but I can print any I can decide on any angle. Basically, you just measure the distances. It calculates the angle. The angle is what matters, and it selects a filter that's done generically in our anechoic chamber using an average of many people and dummy heads. That assuming that your speakers are acting like point sources, and gives you the crosstalk cancellation. Instead of giving you 15 decibel, it can give you 8 or 9 or 10, even 10 dB, depending on the reflections in your room, which can give you a significant increase in your imaging. However, it cannot reach the performance of a custom-made BACCH filter. A custom-made BACCH filter is one done with in-ear measurements. That requires going to the next level, which costs a bit more because that requires that we build these microphones, in-ear microphones, are built here in the lab for you. These are built in. These are scientific instruments used in many measurements at many universities right now and many companies. They're also used for recording. As a matter of fact, Chesky Binaural Plus series was recorded with the last 5 albums were recorded with them. And 2 of these albums won the Stereophile Records of the Year. So these tiny microphones can give you superb fidelity. They're not cheap, but they're handmade. They are hand calibrated, and they have their own calibration. And they're flat within up to 48 decibel, 48 kilohertz within 1 dB when you apply the equalization filter which comes with them. You put them in your ear, and you go to the software right here. You click on ARM. I'm not going to go through the whole maneuver, but you get a fire button here, and you click on fire. You follow the instructions. You get a voice that will lead you. Basically, what the software will do, it will send sweeps from your right and left speaker. It measures this transfer function at your ears, which is all the information the software needs to calculate the BACCH filter for that position. Now, I say for that position because it turns out it matters where you're sitting, and it matters where the speakers are. Now, as I said before, it doesn't matter where you put your speakers, but once you decide where to put them, you make a BACCH filter, and that's it. That BACCH filter will work for that position. Now, it turns out that for most speakers, I can answer the questions later on about the size of the sweet spot. The size of the sweet spot where you have to sit to get 3D image is plus or minus 7-8 inches. For directive speakers, it's a bit less. For omni speakers, a bit more. But typically, you don't need, if you don't mind sitting in plus or minus 7-8 inches, and most audiophiles don't move that much, then you don't need head tracking. But the nice thing about BACCH, we developed a technology that allows you to update the filters by making multiple measurements. It takes only about 3 minutes to make 3 measurements. When you make the 3 measurements, you get head tracking filter, meaning now the filter updates as you move your head. So when you move your head, you can move way past the sweet spot that would be the case if there's no head tracking. And you get a 3D image irrespective of what your head is. And this technology is also patented, and it's very effective at giving you 3D image with a very robust, that's very robust to head movements. We also use the same head tracking technology to update the room correction, which I haven't spoken about today because I'm focusing on the spatial imaging. But if I get the chance later on, I can explain what we can do also for room correction based on in-ear measurements. But just to summarize, this software can do easily, can produce custom-made crosstalk cancellation filter that can give you crosstalk cancellation level in excess of 15 decibel. It turns out you don't need more than 8 decibel, 10 decibel to reproduce in 3D most acoustic recordings and pop recordings. So 8 decibel is plenty, and it will give you a significant improvement over regular stereo where the image is phantom image stuck to your speakers. Finally, I want to say a couple of words. Everything I've been saying is in the context of acoustically recorded real imaging. Most music, as you know, most commercial music, 95% of it at least, is recorded artificially by panning. We can discuss, and on our website, there is a section called FAQ. You can get to it from the bottom of any page, where there's a detailed discussion on why a BACCH filter can enhance the realism of not only acoustically recorded music, but also pan-potted music. The reason why it can is as follows, because when mixing engineers record, they are actually creating, at least when they do a good job, they're creating a simulacrum or an imitation of a spatial image based mostly on the interaural level cues by doing panning. And that interaural level cues is enough for BACCH to translate into an extraction into a 3D image. The key point here is that the extraction is done at no cost to the tonality, and most importantly, is at no cost to the balance of the image. So it does not affect where the guitar is in the mix. It does not affect what the drums is in terms of amplitude or location in that mix. It extrudes that image into 3D. The image is artificial in the first place. It's concocted in the first place. But if it's concocted with some realism, it will be extracted in 3D with some realism. Therefore, it's almost never, we never had anybody complain. It does happen in extreme imaging but most people who listen to pop music with a BACCH filter never complain about the image becoming more three-dimensional. People who have not listened to BACCH ask a question, which is a very valid question until you consider the answer I just gave. When the music was recorded, the engineer did not intend it to be that way. He did not mix it on a BACCH monitored system. The engineer mixed it on a system that has crosstalk. Therefore, we should respect the engineer and play it on a system without crosstalk cancellation. That's the purest attitude. But the point I'm making is that when you add crosstalk cancellation, which, by the way, you can tune down if you want, although very few people do by this level right here. If you add crosstalk cancellation, in other words, if you reduce the crosstalk, the image will extrude into 3D, which is something people do a lot of things at home try to do when they talk about holographic imaging. They're actually trying to do exactly that. Crosstalk cancellation can do it very effectively and give you a three-dimensionality that is indeed artificial, but it's starting from an artificial image that's becoming more artificially 3D, that if it doesn't impact the tonality, and if it doesn't impact the balance, which BACCH does not, then it should be pleasant and very satisfying. And this is what most people find. And it's best when people are adamant about that question, it's best to ask them to sit down, play their favorite kinds music, multiple tracks, and they'll convince themselves very quickly that whether it's acoustic recording, where the realism reproduction is undebatable and unambiguous, you feel that you were there, especially with reverb. Reverb is one of the most important aspects of recorded sound that, if reproduced in 3D, can be tremendously satisfying. We take it for granted that it's not correct with regular stereo. It comes most reverb. Most systems going to give you reverb coming mostly from the speakers, but with crosstalk cancellation like BACCH, correctly, it comes from around you, and that reverb reproduction can be incredible at feeling realism right away. So that happens whether it's recorded acoustically, or in many modern recordings, people now add what's called convolution reverb, which is really realistic reverb, which has a lot of the decorrelation aspects or the uncorrelated left and right ear information that happens in real reverb. And when that goes through BACCH, even if the music was all concocted by pan-pot mixing, the envelopment and the realism is so rich that it's hard to live without it. So to summarize, I think what I tried to portray today is that stereo, on one hand, is a wonderful thing because it has, luckily, the techniques used to record stereo preserved ILD or ITD information. Imagine every movie ever recorded was recorded in stereo by, in 3D. And just happens that we just now found the right glasses to put them on and watch 3D movies. With BACCH, it's as if, however, it works better than 3D imaging. Because 3D imaging has a lot of problems, especially causing dizziness. But with the 3D imaging with the sound, you don't have that problem. So having something like BACCH is like having a 3D image, 3D glasses arrive to watch all the movies done since the invention of cinema, had there been recorded in stereo. That's how lucky we are with stereo. It was recorded correctly. The information is there. The crosstalk corrupts it. BACCH can correct that corruption and allow your brain to get some of those cues to a large extent. Now, there are some limitations, of course. We can talk about that in more detail. I know some of the questions regarding reflections. So I'm going to stop right here.
Edgar, let me just say that was fantastic. Hadn't seen that presentation before. I didn't realize that I was going back to college, but clearly we all were there, and that was really enlightening. That there's a ton of questions that are coming on. I think it would be now a good time to pivot towards that. But before we do that, can you unshare your screen? Because I just want to give people a little bit of, if I can, hold on one second. Where is it? 3. Yeah, a little bit of context on your products, just to make sure people get it. As Edgar said, the BACCH for Mac is kind of the intro into the technology now. If you scroll down, this is on your website, as you mentioned, there's an intro, which is under $1,000, but it doesn't use actual measurements that you're taking in your ear. So it's an approximation. I would say that I would advocate that you should skip over that unless you're really, really leery about it. Because I think where you'll see the big gains is when you take into consideration your own unique setup, your own unique pinna, all those sorts of things. So most people, I think, jump to the Audiophile, which is what I have. That's why I said it was slightly up from the bottom. It's about $5,000. You can then add Headphone technology, which you can go on the website a little bit more. You can increase the quality of the microphone for measurements. It's a little bit more, but that's kind of the BACCH for Mac setup. If you want to, and as Edgar mentioned, this was done so that he could bring the price down and frankly allow some of the computing to be done by the Apple Macintosh, Mac Mini, as opposed to having to build everything by hand at a small volume level. But those that are sort of on the higher end of Edgar's technology, if you look at the top here, we've already talked about the BACCH SP. That was the very first product. There's the flagship model. He's also got two other versions that are most of that technology. One has a DAC in it, one does not have a DAC in it. So that's more of an all-in-one encompassing version, but at a lower price. And then there have been other technologies that have come out about a year ago. Obviously, Edgar talked today about crosstalk cancellation, but he added room correction, optimal room correction technology about a year ago. And that kind of just took the things that we've seen in other software products, I think, to a completely different level. So now, if you have that module built into your BACCH for Mac, you're getting both the crosstalk as well as the room correction. There's even two new technologies that we're not going to talk about today, just so you know it's out there. There's this relatively recently, within like the last couple months, there's been this product called the BACCH Stratos. It's essentially trying to emulate a Dolby Atmos 7.1.4 speaker system, but only using two actual physical speakers. Pretty incredible. And the last one here at the top is the DRC2, which is a desktop, the ultimate desktop spatial audio speaker system for sitting at your computer and getting a lot of this technology. So there's a whole range of products here. We've really only focused on the crosstalk filter capabilities, that for at least most people, I think, Edgar, is people get access to it through the BACCH for Mac. Is that correct?
Yes, very much so.
Yeah.
Thank you, Todd.
Yeah, so I just wanted to orient everyone there. Please go to the website and look at that. But let's jump into, some of the questions. And I think some of the ones that I was thinking about, you already sort of covered in your talk. So I'm going to rip through a few and then we'll open it up to folks. But you talked about this technology, and I think one of the questions is, we've heard for so long about room correction, room treatments, and specialized, technologies that you need to fit this out. Do you need a highly specialized, listening room to benefit from BACCH, or can it work in a regular environment?
Yeah, that's probably the number one question. I'm glad you asked it, on many people's minds when they come to consider a technology like BACCH. It turns out that the only requirement is that, to put it in a simple English statement, is that you're listening to your speakers and not listening to your walls. Okay, basically, is the ratio, more technically speaking, is the ratio of direct to reflected sound has to be high enough. How high? Just high enough. In most audiophile systems, is quite high, meaning that you are not really listening to the reflections in your room as much as your speakers. If you put your speakers 15, 20 feet away from you, near glass windows and near a wall, and sit, very far away near behind you another wall and glass and so on, you can take a measurement. We can take a measurement with BACCH for Mac, and you can see the impulse response, and you can see that more energy is coming to your ears from the walls than from the speakers, and that means the ratio of direct to reflected sound is very, very low. Very few audiophiles, if any, who are worthy of the name, have such a room. Now, of course, there's a whole spectrum of people who have rooms that are very live and not very live. All you have to do to ensure that you have an adequate enough level of ratio of direct to reflected sound is to make sure that you are absorbing the early reflections. The early reflections are the nastiest. Your brain, any reflection that comes to your ear about 20 milliseconds after the direct sound, your brain hears it as an echo. It doesn't mess up the imaging. It's the one that happened earlier will smear the sound and will mess up the imaging, and so also it will lower the crosstalk cancellation. Therefore, you need to absorb them if they are strong. I would say 80% of my customers, 75% don't have room treatment, but because they happen to be listening to the speakers and everything works fine. Some have live rooms, some of them have very well treated room. What you want is to absorb any strong reflections if they exist. Okay, but in general, most systems have high enough direct to reflected sound, except those are ridiculously not well thought out, where people put speakers inside the walls and sit very far away, which is not the case for most people, I'm sure, in this forum.
I can tell story. First of all, one thing that's really important to reinforce is that you're one of the only products that actually measures at the ear, which is where we listen. When you use things like RU, you're using a single microphone, and you're not getting the binaural audio, so it's much more accurate when you're using the way we actually listen. The second thing I'd point out is that several people have used your technology to figure out where to put their acoustic treatments, as you just mentioned. I can say that when I ran my numbers initially, I had a lower crosstalk cancellation than I wanted, but when I put in some panels at the first reflection point, I immediately got a jump in the crosstalk cancellation. And by running the measurements, I could actually move the panels in the first reflections and dial in the exact location where I could get the best performance. And again, it's quite easy because it only takes a minute or so to do a measurement.
Exactly. The software can be used as diagnostic. If I can share again just quickly, and I'll show that. Basically, what Todd was talking about is that you can actually get a measurement of the impulse response. This happens to be a very quiet room. So this is the direct sound coming from the left speaker to my left ear, followed by almost silence. Many rooms have activity here. They have another impulse response here, another one here, a lot of dispersion. And with this, when you make a measurement, you can look at the plots. And if you know a little savvy with the speed of sound and so on, you can actually calculate where the reflection is coming from with a little savviness. But quite often, you look around the room, you'll see a coffee table in front of you. That's probably the culprit. And if you put something on it, it will absorb it. Most of the time, it's the walls on the side or windows on the side. But again, as long as that impulse dominates over the impuls impulses, you're fine. You'll get a crosstalk cancellation level that's high enough to give you significant improvement in imaging.
Yeah, that's great to show that plot. So I think a summary of the point would be you don't need room correction to have BACCH work, but if you do add it, you'll get even greater performance because you can address some of the issues that the room has if it's overwhelming kind of the direct sound. So the second part kind of related to that then is, what about different speaker designs? I know some speakers, that are more directional, I think work better. Can you talk about speaker design?
Yeah, that has to do with the same rule. There's only a single rule that's important. You need to have the direct to reflected sound ratio high, meaning you need to be listening more to your speakers than your walls. Now, if you happen to have speakers that are omnidirectional and walls that are untreated, and you're sitting very far away, that leads to a low ratio of direct to reflected sound. And that will lead to lower crosstalk cancellation, and BACCH cannot get you as much imaging as it could if that wasn't the case. The opposite is that if you have very directive speakers, then you can put them in a room that are quite live and benefit from having very high crosstalk cancellation without having to worry about your room. So there's nothing inherent about the speaker themselves that make them work with BACCH or the other. It's the combination of how the room and the speaker give you the combination of how much the ratio of what they give you in terms of ratio of direct to reflected sound at your ears that matters. Like I have a customer who just wrote to me today, by the way. He has MBL, has the MBL extremes. He's a wonderful customer, lives in New Orleans, has a beautiful big house. MBL extremes. They are the worst speakers, technically speaking, for getting back from getting the high level of direct to reflected sound. Okay, because they're broadcasting sound around the room. But he has spent a lot of time treating that room, and the room is quite large. So effectively, where he sits happens to be very high level of direct to reflected sound, and he gets very high crosstalk cancellation, and despite the fact that he's using omnidirectional speakers. So it's really people ask me, what speakers should I get? Get speaker that go with the room in such a way that you're not listening to the walls. Do not buy very expensive speakers and end up listening to your walls. That goes whether you're using BACCH or not. That should be very clear. Now with BACCH, you pay a big price for it because you will not benefit from the image enhancement if you are dominated by the reflections. Now the reflections have three detrimental effects. One of them, they mess up the imaging and decrease the amount of BACCH. The amount of crosstalk cancellation you can achieve with BACCH. That you cannot do anything about unless if they are too strong, you have to absorb them. However, luckily, the other two detrimental effects of reflections can be dealt with DSP, and that's what room correction does. The second most important detrimental effect is that it messes up the frequency response. Reflections will come at your ear at different times. There'll be cancellation, there'll be a diffraction pattern, and there'll be comb filtering, all of that, and there'll be room modes at low frequency. All of that can be corrected with DSP, and we have a technology that does that at your ears and does head tracking to correct for it. And the third thing that third bad thing that reflections do is that if they're strong, they are adding more energy at different times. So the impulse is being time smeared. The sound is not, instead of being very sharp, is appearing at different times. Not enough to hear it as an echo, but enough to make it less sharp. If somebody plucks a guitar string and you have so many reflections in the room, instead of hearing a single pluck, they'll hear a smeared sound. And that is the other thing that you cannot do anything about except with absorption. So to summarize, it doesn't matter what speakers you use as long as reflections do not dominate. And if you have reflections, you can deal with their bad effect on frequency response with room correction, especially if you have advanced room correction. But there's nothing you can do except absorption if these reflections are too strong, and because they will mess up the time transients, and they will also lower the amount of crosstalk cancellation you can achieve.
Edgar, I'm going to combine a couple different questions. People have already invested in technologies before they heard of BACCH. I, for one, had invested in Trinov's Amethyst, which did some room correction. Other people have done room measurements and maybe are using some sort of DSP already. One person here had said that, I'm not sure if this is technical because I don't know the Wilson speakers, but they're dialed in for timing delays. I guess some sort of technology with Wilson. So what's your perspective on BACCH in relationship to all these other technologies? Is this the sort of thing where you need to throw away the other technologies and
Not necessarily. As a matter of fact, we let people decide, but we guarantee them that whatever they have, they can leave it downstream of BACCH and make a BACCH filter with that room correction that you have. It's guaranteed to improve it. Why? Because none of them are working binaurally at the ear, and none of them is tracking your head. Most room correction depend on you taking a microphone and making multiple measurements, and the software takes these measurements and averages them. An average is by definition wrong everywhere. Okay, so instead of relying on something that's wrong everywhere, we measure it at exactly your ears, track your ears very accurately within sub-millimeter tracking, and then compensate based on where your head is, so that at your ears you're always getting the right correction. None of these technologies do that. Plus, the way we do room correction is radically different. It has to do with the correction both in the It's based on the morphology of your ear. It locates the pinna notch in the frequency response that's individual for every person, and treats the frequencies in the high in the what's called the high order pinna, the low order pinna, which includes your head, and the free field, which includes the room, separately, because the room absorbs high frequencies, and if you compensate based on the integrated response, you end up boosting the high too much. So basically all the other technology, they all do something very nice, very correctly, but none of them can do what we claim, all the corrections that BACCH does. So you can leave them, and on top of them, let BACCH do its thing. It will improve it. Now you can take them out and let BACCH do its thing, and you'll find out that the result will be somewhat equivalent, because it's going to try to correct everything in terms of the frequency response, and make it more natural for human ears. Therefore, if you leave your existing technology, and we have tested them here, we have Dirac, we had Trinov for a while. They're all very good technology. A lot of great engineers went into a lot of human hour time went into developing them. I have a lot of respect for these engineers. But I'm saying that our approach is more is different in the sense it's binaural and head tracked, and we claim that if whatever you have, if you add it on top, it will improve. And if you decide to A/B them, you will most likely find out, this is a claim you can verify, that if you A/B case A, where you have BACCH with other room correction working in tandem, and BACCH by itself, the difference is not very large.
One of the things that we've talked about a lot is you have to know a lot about the individual person listening and where they are and what their makeup is in terms of ear dimension, et cetera, which implies that the system is designed for one person. Can you speak to the fact that
yes,
while many audiophiles, myself included, my family wants nothing to do with listening with me when I listen, but other people, do. They have multiple people on the couch.
Exactly.
Explain first of all, what they experience, and second of all, can you crack the nut of multiple people getting a BACCH experience?
Yeah, this is a very good question, and one that's been haunting me for years, and I have some good news. So first, to answer the first part of the question, if BACCH is a single, right now, the commercial available BACCH is a single sweet spot technology, only the lucky person sitting in that chair, and it turns out people behind that person, in front of that person. Why? The sweet spot turns out to be, for technical reason, quite narrow, about 7 to 8 inches. So if you move your head like this, you're not going to hear much difference. If you move forward and backward, it's even more tolerant. Depending on the directive pattern of the speakers, the more omni, the more you can move forward and backward. You can move more than 2 feet or so, 3 feet. This is why if you come to the shows, you will see in our rooms or rooms that have BACCH demos, people lined up behind each other in seats, because the person sitting in the sweet spot is getting 100% image, 3D image. The person behind him is getting a 90% image, and the person behind that person maybe 80%. So, but if you go to the side and left, if somebody's sitting next to you, they're getting 0% if they're outside the sweet spot, let's say 10, 12 inches. So unfortunately, the person sitting outside is not getting BACCH. But the nice thing about BACCH, because the filter is perfectly flat, and that's probably the number one characteristic that makes it compatible with our goals as audiophiles, is that there's no penalty. So the person standing outside the sweet spot is getting as if there's no BACCH. If you turn the BACCH filter on and off, bypass it, that person cannot tell. We do that to convince people that BACCH filter is perfectly flat. And this is why that person will be listening to that system without BACCH, without 3D imaging, but with the full beauty and glory of whatever that system can deliver without BACCH. There's no penalty. And to the point that if you turn off BACCH, that person cannot tell. Now, can we do something about it? I have to tell you that when we started, BACCH existed. Crosstalk cancellation existed before 2012 when I started, 2007 when I started playing with it, and it was wonderful technology, but it was only for the lab. The first problem we solved is the one I talked a lot about, is how to do crosstalk cancellation without any spectral coloration, and that's what the patent came through, and the main breakthrough came through. We call it BACCH. Then the problem was a single sweet spot, and if you move to, you will lose it. And then we developed this head tracking called HT BACCH or head track BACCH. And I give you them, and many of our customers use head tracking, especially those with directive speakers like myself. I have directive speakers. I use Jensen speakers. They are quite directive, and this is why, because my room is very live. I do not want to treat it for aesthetic reasons. So when I move my head, I need head tracking. Now, the next improvement is how to make it for more than one person. So I'll share with you something that we've accomplished now about 4 years ago, and it's about to become from a major company, become a commercial product. Why it's not great news yet for audiophiles will become clear when I show you the picture. So we were able to solve the single sweet spot problem using phased arrays. So here's a phased array. Is a multiple series of speakers. So here is a schematic. So basically, the bird now can be reproduced not only for one person, but for multiple people. So every person will hear a bird, because we can use a phase array by controlling the delay between the speakers and the wave front. We can create beams of sound. So you can I drew the beam like in white and blue and red. Imagine almost like flashlights of sound shining at your ear, and by head tracking we can direct those beams to your ears as you move. This has already been discovered. I mean, it's invented and developed and patented, and it's called BACCH. So BACCH is now a technology that is finally coming to the consumer audio sector because it requires a phase array. Unfortunately, you would need many, many speakers to have it to work. Most of us in this group, in this forum now, only have 2 speakers. So this is not compatible for us. But the big news is that the problem of producing, let me go back, let me stop the sharing. The problem of producing multiple sweet spots without phased array has been declared impossible for mathematical reason. It's actually called an overdetermined problem. You have 4 ears and 2 speakers. You can show mathematically that it's impossible to solve it for the entire frequency spectrum. The word impossible in audio has been going out of business the past 2 years only. And this is the big news. This lab behind me, and there are 4 rooms behind me, all the graduate students who are now, for the past 3 years, are studying first AI, neural network, and neural and deep learning, and then acoustics. And they're using more neural network than acoustics, unfortunately, for people like me who can teach them only acoustics and audio. The problems that we declared unsolvable 4 years ago are now solvable with AI. I'll give you one example. We had a grant from a company called Focal. All of you know who Focal is, to produce not only multiple sweet spots, but 2 sweet spots that can play 2 different programs separately, called personal sound zone. So you and your spouse could be in a car. He or she could be listening to one program. You can listen to the other without headphones. So we developed that technology using beamforming and using inverse filtering, and it works beautifully. And we achieved the record of 30 decibel crosstalk cancellation. So you can basically blast music and your partner can go to sleep in the car without listening, barely listening, 30 decibel down. Or she can hear a choir, you can be hearing Led Zeppelin next to each other, and you can barely hear each other's program. That worked beautifully, except if you move your head a tiny bit, the whole thing would collapse. So it was kind of a demo for the lab, and it was not really practical because we showed that to track head movements, it's impossible. There's 6 degrees of freedom per person, and to do all the calculations and update the filters so you can have that personal sound zone be maintained while people are moving their head, mathematically was impossible. As I said, the word impossible going out of business because all it does today is to know how to design neural network and train them to do things that we do not know how to do analytically. And the personal sound zone has been, with moving heads, had been completely solved. And now it's called Brahms. and that technology is also coming from a major. I cannot tell you, it does require phased array, and it does work with head movements, but it does work basically because of deep learning and a lot of this is neural network that we built from scratch and trained the heck out of. I trained it to the point where it does beamforming better than analytically beamforming can work. The good news is that only recently, and this is my punchline, and I'll stop in 1 minute, we were able to apply this with very promising results to get 2 sweet spots with moving heads from 2 speakers. So this is the first time I announced it publicly because we're not getting sure that it's working. So I'm hoping then within a year, we'll be able to have multiple listener with BACCH with high enough crosstalk cancellation with head tracking from only 2 speakers, like the regular 2 speakers. So, and I have a punchline. I have a name for it. It's called BACCH WAF10. And for the WAF10, it stands for Wife Approval Factor 10. It allows my wife to enjoy BACCH with me.
Aptly named. Well, we all heard it here first. Breaking news. So that's awesome. I want to keep on going. We got a lot of questions. One conclusion that people may take from this talk is, oh, this is all for like digital music, streaming, CDs, etc. Can you speak to, for those of us that are vinyl enthusiasts, how does this work for vinyl?
I'm a collector. I collect master tapes and master dubs. I have about 500 master dubs, and I have and many master tapes, and I have a few thousand vinyl. So I love analog, mostly for the tactile and for the. I grew up, with the big real estate albums. I love them, and I made sure that the first product I did had a very good A to D converter for people who have vinyl records. And I don't listen to any vinyl record or any analog source without my BACCH. And many customers of mine have analog sources. As a matter of fact, I have a number of customers who have listened only to analog. So analog, as long as you digitize it correctly, and today you can do 64-bit conversion and DSP to the way that you literally cannot tell a difference. You can do A/B test under very controlled environment, and digitizing. I think Fremer is one of the people who believe that if you can digitize, he's one of the champions of analog audio. He strongly believes in many years ago. I think you should give him the credit. I came late to that belief when I realized with good A to D converters, you can really get analog to work. Once it's in digital domain, and you can do this magic DSP. Finally, this DSP is done at such high resolution, done at 64 bits, at calculation that years ago would cost a building of supercomputers. Now we can do it in a Mac Mini. So there is absolutely no audible degradation to the sound, or I should say, added coloration or anything that would detract from vinyl analog lovers too. So I invite analog lovers to be wary of such a technology just because it's digital.
As Edgar can attest, I have many sources in my system. I have CD transport, streaming, digital files, and a gigantic vinyl. I have actually 2 mono turntable and a stereo turntable, and Jim can attest, since he's actually been at my house. We've played it all different formats, with and without BACCH. One of the great things about BACCH is there's a bypass button, so you can just turn it off and then turn it back on and hear what BACCH is doing. And
yeah, I could say I'm very proud of that bypass button. I'm going to show it again here. Let me share the screen. I'm glad you brought it up. This bypass button, I claim that if a lot of technologies have it, if every cable had a bypass button, I don't think we'll be selling a lot of cables. But as you see, at any point, you can click on bypass. And that's your stereo before BACCH. What comes in, comes out. So you can judge if there's any A/B instantaneously.
And what you'll learn, using that, and what we've learned and Jimmy, correct me if I'm wrong, but what we hear is that tonality wise, we don't hear a difference really between it on and off. And the same, but what you do hear is the spatial, the imaging just radically changes, the depth, the imaging, the pinpoint, the sound stage, etc. Just expands, and it seems to have an equal effect whether the original source was a vinyl record or the original source was a stream or a digital file. So yeah, but you can prove it to yourself by just using that bypass button.
Yeah, we encourage people to use the bypass button. You do that initially. Whenever people install BACCH, the first day it's all they do, and after that they don't touch it. They never go back to it. Instead, unless if they're demonstrating to friends what's going on. But once you go back, you don't go back.
Is that trademark yet? So
I think I just came up with this right now.
There's a couple questions here that I think have to do with representing the room. So I think they're related. Somebody wants to know about ORC, which is optimized room correction. Does that negate the need for timing delays? I assume he's talking about timing delays within the speaker system, et cetera. Maybe you can address that. But I think it's related to maybe some other questions, which is, when you're using BACCH for, let's say, a recording, which was done in a huge venue like a cathedral, how does that your technology affect the sonics that you're hearing, in the room? And specifically, how is your technology dealing with height and depth cues, not just, your presentation mostly talked about left and right, but not as much height and depth.
Yeah, there are two separate questions. I'll get to room correction in a minute. But first, because that question you just asked at the end have to do with imaging and realism. So reverb, as I said, is very important. And the fact that without crosstalk cancellation, you will hear it stuck to the speakers. This is why people ask you to have some dispersion in the room, a live room, to tow out the speakers a little bit, to splatter sound around the room to get you some envelopment. With BACCH, you don't want to do any of that. You want, as a matter of fact, listen to your speakers as much as possible. And the crosstalk cancellation will ensure that you'll hear the reverb in the recorded venue, presumed it was recorded correctly, or in the convolution reverb, which now is done for most, pop music. In both cases, you'll get the 3D reverb that envelops you, and your brain will get information of height also because of our experience of how when uncorrelated sound comes in, we feel that we are in closed spaces. To get precise height information, and I have a few slides based on that. I was going to go there, but if you want me later on, I can. You need to go to binaural recordings. So I have a bunch of slides because I saw that early on. You mentioned that you might ask me about the future of how things should be recorded down the line, how to even improve 3D, how to make it super accurate. There are techniques that a lot of people in my community are working on. Starting from binaural recording is one that's done with a dummy head. That has this addition to the ITD, ILD, has spectral cues that allow you to get height information. But that is not enough because the humans have a mismatch between their head they're listening with and the head used for the recordings. So we have solutions for that too, while we record with the HOA microphones like the one behind me, and then integrate at the end during the playback, we can inject the HRTF of the listener, individualized. This is a whole new idea of how to listen to music, new paradigm, which will become reality, and it's becoming reality in the VR world more than becoming more the audiophile world. But to answer the question fully, regarding the reverb, we can get reverb to feel really 3D. To get localization with height, some of it is already can happen naturally because the ratio of direct to reverberant sound in the recording gives you some height information and gives you some depth information. The proximity can be gotten very accurately if you have high enough crosstalk cancellation. So you can get proximity, you can get some height information, but to get sound appearing right behind you, you have to have individualized measurement, and in other words, you have to have the recording done with your head. This is how why Stratos works, because we actually record with your head the speakers in front of you to reproduce the Atmos speakers. So in other words, it's with regular recordings, you're not going to get. Luckily, most regular recordings do not have people singing behind you. You're not going to get people singing behind you very precisely with crosstalk cancellation, but you're going to get a 3D image that's far more 3D and realistic than stereo, because your ears are getting the reverb correctly, they're getting the azimuth location correctly, and some height information depending on the cues already in the music.
Edgar, there's quite a few questions about maybe some of the other modules that you have. Can you spend just a few minutes talking about ORC and what is so unique about your approach there? And then secondly, we're going to talk about the headphone module and what's very unique about that. So maybe a few minutes on each of those.
Great. Great. So ORC exists for both the BACCH SP and the BACCH format. By the way, everything we develop, we start with the BACCH format because it's easy to integrate, and then when we make it robust and stable and upload it to the BACCH SP. So now the BACCH ORC, which came about 2 years ago, exists for both. So the way it works, you make a measurement the same way, in the same time when you make a BACCH filter measurement, and then you can go to the ORC module right here. And you can see it's tracking my head in 3D. When I move my head, it knows where my head is, where my ears are in 3D. Okay, so it knows exactly where I am, and it knows it shows what the frequency response measured. This is my speakers in my listening room, and you can see this is not flat. Why? Because it's measured inside my ear. That's a binaural measurement, so it's never going to be flat. It's going to be flat only at low frequencies. At high frequency,
hey,
Edgar,
notch. Edgar, we're not seeing the ORC panel.
Sorry. Let me go back and share the entire screen. That's okay. I'm glad you stopped me there. What about now?
Yep, we got it.
Okay. Yeah, sorry about that. So let me start very quickly from again. So ORC module, you can turn on. Thank you for letting me know. We'll show you first that you are tracking your head in 3D, and it knows exactly where your head orientation, where your ear are, and it's compensating in real time. What it's doing is correcting this measured response. This is a measured response at your ears. It's not flat because it's measured at your ear canal. Therefore, it has a notch. This is called the pinna notch. My pinna notch is about 7.5, 7.6 kilohertz, which is right here, for speakers at plus or minus 30 degrees. That's typical of many men. Women have a higher pinna notch on the average, depending for the same location. There's different between Caucasian men and Asian men and so on. But this is a lot of, this is because of morphology of the ears. But whatever it is, a BACCH ORC will find it and will treat everything above that as something called high order pinna and applies a certain algorithm to correct for it. And then everything between that and about 1 kilohertz, where your head effects start becoming less important, as something called low order pinna. Below that frequency, the wavelength is so long that your head doesn't matter anymore, your torso doesn't matter. The frequency response should be flat. And as you see, it's not flat here. That room has some reflections. There's a room mode right here, and then at the end, the speakers don't have subwoofers, and the bass drops. So what ORC does, it corrects for all that. You can see here, I left behind in shadow the uncorrected room, and you can see now any asymmetries were taken out. The correction at high frequency is slight, but it's done optimally. But starting at 1 kilohertz now is flat. It's completely flat, and it's all the way down to about 25 hertz, 35 hertz. You can actually boost the filter more, like 6 dB, recompute the filter to make it even flatter if you want, at the price of reducing the volume. Most high-end audio systems have plenty of headroom, so you can afford that. Now I give it 6 decibel boost. I'm going to make it even flatter. So now, when this is done, you'll see here how flat it is. So compare that to what it was. Not only is flat like this, it's flat like this wherever you move your head, because we flatten it as all the time as a function of the head location. So that's what's revolutionary about this technique, is that it's binaural, it's head tracked, and also what I didn't mention is that we are treating the early sound and late sound completely different, because they should be treated differently. They contain different contents, so you cannot equalize it the same way. The bottom line is that you're going to end up with speakers that sound completely different than before. As soon as we design a ORC filter, we play some voices and show people. You can automatically bypass it by going here and bypassing ORC on and off like this. And when you turn it off, you hear without it. When you turn it off, you hear this. When you turn it on, you hear that. Okay, you hear that. So it's you can hear night and day difference right away. You can also bypass both ORC filter and BACCH filter. You can turn on the ORC without turning on the BACCH filter, or you can turn on both and forget about it and listen to your music with a completely transformed system. So the ORC have been really less controversial than BACCH, because nobody debates, the fact that we're correcting it. BACCH, it takes quite a bit of time for people to wrap their head around it. There are always going to be people saying, wait a minute, that's not what the engineer intended. But no engineer ever intended for your speaker and room to have such coloration that when taken out, it should be questionable. So ORC has been really an incredible success for us in the community. So I love the way that people react to it.
Just one thing I wanted to point out for everyone on that, you don't have to bring it up, but on the ORC panel, you can set various target curves. So if you want, your own personal taste, you like a little bit warmer sound, you can set a target so that it's not, exactly flat in that region. It's tilted a little bit. So there is a lot of personalization that you can do while still doing this room correction. And I can tell you, it's fun to play around with different curves just to see what the impact is on that.
Yeah, as you see, the ORC has a lot of buttons. It looks something out of the lab, and it is out of the lab. However, people get scared of it initially, but all these settings right here, all these settings, they have a white green frame. These are the recommended default settings. If you click on default settings, everything is in the green frame. 90%, 80% of people are fine with that. People who have very deep room modes have sometimes, because of room modes at bass at like 50 hertz, they have a big dip right here or a big boost in the bass. There you may need to increase one of these settings. This one is called the allowable boost for the quasi-free field, meaning allowing the filter to boost more in this low frequency. Now, what Todd was talking about is that there's a setting in the bottom, which, by the way, is the optimum. The recommended optimum setting is what we think is optimum. Now, some people like to have more bass boost, and so after you optimize, you can choose to go to something called olive curve, which will boost slightly the bass and give you more bass. There are a lot of psychoacoustic measurements done. Subjective measurements done by Bob Katz and by the European Audio Society and by David Chesky and by myself, that's TAP. I actually prefer Katz, believe it or not, over after I came up with they're all different curves. There are very slight differences on how you treat the high frequency, but leaving it in the optimal, is what recommended initially. But as Todd said, if you listen to some pop music, you might want to shift the curve down. So with what's called Sean Olive curve, that will give you slightly more bass boost and give you more bass richness.
Yeah, that's exactly right. I'm gonna rip through a few of these that are pretty easy, just in the interest of time. So people are asking about the integration with video, TV, projectors, etc. Many people use this system with TV, so it can be used in that way. And Stratos, which I told you was an emulation of Dolby Atmos, I think it's now early stages, but I think the intent could be to is very much to be able to replicate while you're watching a movie out of two speakers this type of sensation that you get from a Dolby Atmos setup, but at a fraction of the price, clearly. A few other things. Do you need to recalibrate when you change speakers and components? The answer is yes. I recalibrate all the time. I change one darn thing, I recalibrate, because recalibration is so damn easy. It's usually like a minute, and it's quite easy to do. And I just feel better that it's using the very latest environment that I've created, and it's not a big lift to calibrate. I'm sure Edgar would say that you don't have to do it as much as I do.
Well, I mean, Todd, you are on the one end of the spectrum. You're an engineer.
Yeah.
I have very smart customers who are not engineers, of course, and who'd rather not calibrate every night. Now, you're absolutely right. If you change the speakers a tiny bit, you should recalibrate. If you move the camera a tiny bit, you have to recalibrate. However, most of my customers don't touch their speakers. That's it. And a lot of them who are genius at what they do are not technically minded, and they rely on me to do the filters during the walkthrough session. And until they change their speakers, they don't call me. We have people who are every night make a filter, and these are the other, and even beyond Todd, who do it every night. No matter what, even they don't change anything, they just like to make a filter. You don't need to do that. But we have people who never make a filter again because they never touch the speakers. And then whenever they have new speakers, they call us because they don't know how to make a filter. And then, even though it's quite simple, but it's not their cup of tea, and we give full tech support. Unlimited time. Whenever you want to make a filter, you call us. We'll help you make it. And as long as you have your service, which is renewable every year, or for the BACCH for Mac, or 3 years for the BACCH SP. So you have that service. We'll get on it quite often, late at night, and help you make filters if you want to solve problems.
Edgar is very available. I don't know how he does it, but he's very available. We're running out of time. We're running out of time, so I'm going to ask two last questions. One is, there's quite a lot of interest in the headphone module. I don't have that.
Great. Well, let me say something about headphones. I mentioned early on that I'm not a headphones guy, in the sense, unlike my students who are 40 years younger than I am. They all have headphones and earphones, and they love working with me on headphones too. As a matter of fact, this is our headphones lab here. I don't know if you can see, but these are all headphones hanging on their headphones everywhere. But what we have a technology called BACCH HP for speakers lover like me, like most people in this forum, who happen to want to listen to the speakers late at night. I also live in Manhattan. In Princeton, I can blast my music, nobody cares. I live in a house. But in Manhattan, you can't. And people will complain right away. In Manhattan, people can complain very vociferously, as you probably know. So I have to be very careful. So for that, I created this technology called BACCH HP. And you make a recording, you can make a measurement using the same in-ear microphones. And when you're done, and you will you'll play anything through your system, but without, instead of sending the audio to your speakers, it will come to your headphones. But the BACCH HP filter will produce a signal at your ear that is exactly the same signal you would receive if you were listening to speakers. So your brain cannot tell you're not listening to your speakers. Quite often, now, every time I do a demo for a customer, or after we install BACCH HP, I play them a dog. I play them a dog from the headphones, and then I tell them, now I'm going to play it from the speakers, and they say, perfect. And I tell them, no, that was not from the speakers. That was coming from the headphones, and they cannot believe it. They turn their head, and it's still coming from the speaker. In other words, we can emulate the speakers perfectly. Plus, we can emulate the speakers with the BACCH filter. So you can listen to the speakers emulation as if you listen to the speakers where the speakers are dead, and you can listen to the speakers in 3D as if they have a 3D BACCH filter on. And this has been a wonderful setup for people who want to listen at night, and for people who want to take their system with them. For example, you have another home, you take your laptop, and then you're sitting in your other home on the beach with your big Wilson speakers, listening as if you're sitting in your listening room, as long as you have good enough headphones. The headphones, it works with any open headphones. The headphones don't have to be anything very special for this to work. And that's another $1,000 more than the Audiophile. It's called Audiophile Plus. We separated it because not everybody needs it. So we decided to keep it separate, and people who want it can add it at any time.
Edgar, before I ask you the last question, I'm going to knock off two quick questions. Somebody asked, how does this actually get hooked up? I just want to point out that there on the BACCH for Mac page, there's a nice little diagram that shows that. You can select what type of sources you're using and what type of speakers you have. But essentially what you're doing here is that the system has a audio interface. You recommend audio interfaces from a company called RME. You essentially plug all of your sources into the audio interface, and then the interface sends that music into your Mac Mini where it gets processed by the BACCH, and then it comes out into the audio interface and then gets sent to your speakers or your DAC or wherever it is. And so
that's one way I should correct. You can also send the audio directly to the Mac without going to the interface, and the Mac can send it directly to your DAC without going to the interface. So the interface can only be used for the microphones, and that's most of the our customers do it that way. Like they have streaming room directly to the Mac, or USB or some other source directly to the Mac, but then they use a USB asynchronous directly from the Mac without going to the interface. So the interface is only used for the calibration, and we use also a software for looping inside, but we don't use, most of our customers do not use it as a DAC, although it has a very good DAC inside.
Last question for you then is, you've answered a lot of questions, but let's just look at a little bit into the future. We heard about one breaking news story about what may be happening in the next year. If it wasn't obvious to everybody, Edgar's company produces products, through Theoretica, but he also licenses the technologies to other companies who then embed the BACCH technology in there. So that's what I think he's referring to, is some partners maybe bringing out some products. So what can we expect from Theoretica over the next year or so in terms of real products? And then let's go a little bit further. Let's go 5 or 10 years out. Where do you see this all going?
First, I should say that there are two companies, they're sister companies. I'm the president of both, but I really run only one of them. Theoretica is my little baby. We make a product for people exactly in this group, audio people like me, like you, who love to come home and listen to music and enjoy that wonderful hobby. And we make products. Now, there's another company called BACCH Labs. I happen to be the president and CTO, but I don't run it. As a matter of fact, from the university doesn't even allow me to have a position in it beyond a supervisory role. That is a licensing company, and it's like Dolby, and that's the company that's licensing to all these big companies. Hopefully, you'll see a lot of these products on. Already, there are some licenses out there. Some of the companies you might know, for example, Dutch and Dutch, their speaker, their main speaker 3C, I forgot what it's called, already has a U-BACCH filter. There's a TV called Canvas, already you can buy in Europe. It's a high-end TV speaker that you can put your big LED on top. It's a big hit now. I hear it was launched in CES a few weeks ago. It's a big hit in Europe. That has a BACCH filter in it. People have described it, and there's reviews of it. There are two main companies I cannot name because of course, all this NDA stuff. I don't run these shows. I'm the guy who stays in the lab, produces the technologies. I'm the one who puts them in Audiophile. But then there's a wonderful team of lawyers and of engineers and coders who do the technology transfer and the licensing. And that's they don't make products at all. They don't make actual products. They license them. What's coming down the pike? So you're going to see BACCH before too long. You're going to see systems where you can hear multiple sweet spots, but you need a BACCH. But you need special speakers, the phase array. That's going to come first phase arrays for major manufacturers for TV people, for people watching TV, home theater. What's coming down the pike is next also from a major company in the US, one where you can listen to two different programs. This is our personal sound zone. This is called Brahms. So, and this is all AI based. We solved that problem, as I told you, with AI. So you can hear a movie. One person hears in Chinese, the other person hears in English, watching the same movie without interfering with each other, using, again, phase array. That's coming down the pike, and it's already done from the lab. Then what's coming in terms of the lab, I mentioned and announced it here for the first time, we now are comfortable to think that we can do multiple sweet spots, at least two sweet spots with two speakers, with for audiophiles. And that's what I'm excited about next. What's happening also is from the lab point of view, there are some hearing aid technology that we've been working on, very directive hearing aids. So when you go to a restaurant with little earphones, you can look at anyone and you will hear only the person in front of you. You can isolate it from the rest. So if you're having a conversation with someone, you can block everybody else by moving your head. That's been developed here, and it's at the stage where it's going to be go into development. It's still in a research stage. There are also a lot of important work done here and elsewhere, but we are one of the labs working on noise control, of course, how to create quiet spaces. From the recording point of view, we have developed tools, which I didn't have the time to show you because it's not the right community, for producing end-to-end, extremely highly spatial recordings and rendering techniques. So in the future, you will go into your car, and your car will know, either by scanning your head, or any car, even a rental car, acoustically what your head is about. By scanning your head and solving the differential equation called the wave equation about your head, which can take now a few seconds to solve, and produce an HRTF, and then render whatever sound you're using acoustically for you and head track you. So you are be in that environment as if listening to an orchestra, whatever environment you're in, indistinguishable, like a virtual reality. So virtual reality relies on combining the high order ambisonics technique and live HRTF measurements, on the fly HRTF measurements, binaural rendering, beaming, all driven by AI. So in few years, when you go into any environment, you can be transported to another environment acoustically, to the point where if you are either eyes closed, you cannot tell that you're not in that environment, or even better, if you are superimposing on that a visual impression, like with AR glasses. And so it's all being driven by AR, VR. The future of audio is strongly linked to the AR, VR. What's driving the innovation is not the wonderful people who have been driving the preamp and DACs and so on we were working on, but the wonderful young people who do not own these DACs, who are driving the high-end technologies of realism, which I hope we will benefit from. And Theoretica's job is to be sure to take whatever these guys find from the AR, VR world and bring it to our world, the audiophile world. That's my goal.
Thank you, Edgar, for an incredible 2 hours. I think everyone who got from the beginning, conceptual, all the way into specific products and everywhere in between. So I just want to thank you on behalf of everybody.
May I suggest one thing? So if there were questions that were not answered, if you don't mind, Todd, if you can send them maybe to Todd, if you don't mind, if you compile them and eliminate the one that are repeating, if you send them to me, I have no problem. I would be very happy to try to answer them. So this way, no questions remain unanswered, if that's okay with you.
Yeah, that's fine. I assume, Jim, you can get the chat questions once the Zoom is over. I'm also, because I'd rather Edgar work on new technology than answer questions, I can answer some questions for people as well and take off maybe some of the easier ones that I know about. Anything else, I'll certainly send to you, Edgar. But there's also an email address on Edgar's website for, I think it's info at at theoretica.us or something. So you can, there's a lot of ways to get more information, but today was fantastic.
There's also FAQ on our webpage. The FAQ is pretty extensive.
Yeah. So, yeah, lot to learn, but hopefully this was really helpful for everybody. And thank you again, Edgar, for taking the time. We are benefiting from all of your hard work, and it's very much.
Yeah, I saw a lot of questions that I would be happy to answer. Somebody asked a question about tree knob, where it goes in the chain, and so on. So please, if you send me those questions, I will do my best to answer them soon. Okay.
Absolutely.
It's a
Jim,
pleasure
is there anything
on Audiophiles.
Jim, anything last you want to say?
For moderating this, Todd. Thank you so much. You did a great job. Yeah. So thank you, Todd, for moderating. Thank you, Edgar, for fantastic presentation. Very exciting. And yeah, I'm hoping that at some point maybe Todd will allow a few lucky people in the Bay Area to hear your system.
Oh, I should say in that context, we have a 14-day trial period. You get BACCH because if you come to a store, you're going to wonder if it really works on your system. So those of you who are curious can get it. You only waste $200 when you return it, because we have to refurbish the microphone. New Jersey law doesn't allow us to take things that go inside your body and resell it, so we have to refurbish the mics. But aside from that, it's definitely worth it to try it and return it. We don't ask any questions. We get very, very few returns, but whenever we do, policy is no questions. So please, if you are curious, just go ahead and try it on your own system. There's no better answer whether it's good or not than doing that.
And since Edgar will be setting it up most likely for you on your setup call, you'll get a lot of opportunity to interact and learn more about what's going on. With that, Jim, are we done?
I think we're done. Thank you, everybody, for coming today. Again, thank you to Edgar and Todd. Fantastic presentation. Hope to have more of these. If you don't belong to our group, support us. This is what we try to do. I think we're unique in that, and really reaching out to the leaders in audio and fidelity and trying to bring them to talk to us and then record it. And we'll make this recording available once we get it edited, and then it'll be available on our website for anyone who wants to review it who couldn't be here today. So
thank you for the opportunity. Very much so.
Thank you, Edgar.
Thank you, Edgar.